So we're in section 3.4, part 2, and we're going to talk about logarithmic equations. I really like exponential and logarithmic equations. They remind me a lot of using solving trig equations. You have to think in a little different way, and just a different way it makes you think is I find it kind of fun. So we're going to do what we did yesterday with exponential equations, but we're going to do it with logarithmic equations this time. Now, what we're going to use for logarithmic equations, let's write down our reminders of our properties that we're using when we're working with these things. So if we have a to the x, and we wrote these down yesterday, that's just a reminder, a to the x equals a to the y. Tells us that x equals y. So if we have the same base and an equation between two exponents with the same base, then our exponents are equal. Our second one, this is the one we'll use more today, is that if log base a of x equals log base a of y, then we know that x equals y. This is the one we'll use more today. And our log functions and our exponential functions are inverses. So those are, we have log base a of a to the x. That is just equal to x. The log function and the exponential function are inverses, so they undo each other. And the same thing for a to the log base a of x just equals x. So the exponential function and the logarithmic function undo each other. So those are our properties, the main things that we're going to use when we solve equations, exponential or logarithmic equations. So for logarithmic equations, we have we're going to use two main processes. Just like we did for exponential equations, we had a couple of things that we did. Our first one, we want to try to get the logarithm on. That's okay. What you looking for?
The student said he would need an logarithm.
We want to get the logarithm by itself. On one side of the equal sign. And then rewrite in exponential form. So we'll do like we did on the quiz, where we change the logarithmic form to exponential form. So something that we already know how to do. We just have to get the logarithm by itself on one side of the equal sign first. The second way we'll solve logarithmic equations is get one logarithm on each side. And I'm going to say one logarithm of the same base. So they have to be of the same base. That's important. And that's on each side of the equal, each side of the equation. And then we're going to use our rule that log base a of x equals log base a of y means that x equals y. So we want to make our equation look like this rule. We get a logarithm of the same base on each side, and then we can say that the things that the logarithm is acting on are equal. So these are the two main rules that we're going to use. And when we do these, when we work on logarithmic equations, we need to remember a couple of different things. And I'll write those down in just a second. Is everybody good with our procedure? Not yet? All right, are we good? So, just some reminders. Remember, we want to remember our other rules for logarithms. We're going to use those as we solve these equations. So we need to remember our other rules for logarithms. So just because we're solving equations, we don't want to forget our other rules. And our second thing we want to remember is that, and this one is important in certain kinds of problems, if we get more than one answer, so if we have to factor something where we end up with two answers, we have to check to make sure they work. We have to check our solutions. Because often in logarithmic equations we'll get two answers, but one of them won't work. So we may have to make sure we check to make sure that they work. So these are just a couple of important reminders. So all I'm going to do for the rest of this is we'll just do a few examples of showing some of these, showing how we solve some of these. So pretty short today. All right. So our first example, we want to solve. We're solving all of these. 2 log x equals 5. So we're going to, for this one, because we just have the one logarithm, we want to get the logarithm by itself on one side of the equal sign. So I'm going to divide both sides by 2. So I get log x equals 5/2. And now we're going to rewrite in exponential form. So to rewrite this in exponential form, log, when it doesn't tell us a base, we're assuming it's base 10. So to rewrite this in exponential form, this tells me that 10 to the 5/2 equals x. So we're rewriting in exponential form. And if we plug that into our calculator, we get x is approximately, if we want a decimal, 316.228. So we got the logarithm by itself on one side of the equation, and then rewrote our logarithm in exponential form. Yes?
So if it's just log to the x, then you assume that it's log.
Right, if it doesn't tell you a base, you assume that the base is 10. Okay? And that's what the log button on your calculator, the button that says log, is log base 10.
Can you change that somehow?
On your calculator, no. Your calculator will only do log base 10 or log base e. To calculate it, we use a change of base formula, the way that we learned last week. Now, I just want to point out there's another way that you can think about what we're doing here, and the book talks about it. Some books you might see it as a method for solving these. So I'm going to rewrite when we got our log by itself on one side. Log base x equals 5/2. We can think of what we did here as raising 10 to the power of each side of the equation. So kind of like what we did yesterday where we took the logarithm of both sides of our equation to solve it, we can raise 10 to this power and raise 10 to that power. This is called, when you use this, it's called exponentiating both sides. And because the exponential function and the logarithmic function are inverses, they undo each other. So this just tells us that x equals 10 to the 5/2, just like we got here. So we can think about it this way also. I think it's a little easier to think about rewriting it in exponential form, but you can think of raising 10, or whatever our base happens to be, to the power of both sides of the equation. So we can exponentiate both sides is another way that we can think about this. You don't have to think about it this way. For some people that makes more sense than this. So it's up to you. They're both equivalent. Any questions before we do the next example? All right, so let's look at another example. We're solving again. We have the natural log of the square root of x plus 2 equals the natural log of x. Now here we already have a logarithm . We have a logarithm with the same base on both sides. So this one is set up for us already. So if we have a logarithm with the same base on both sides, that tells us that what the logarithm is acting on either side, what's inside our function, has to be equal. So square root of x plus 2 equals x. We can also think of this as exponentiating both sides. If I raise e to the power of natural log of x plus 2 and e to the power of natural log of x, I get x plus 2 equals x. So either way you think about it, it's the same thing. Now to solve this, what do I have to do to solve this? How do I get rid of that square root? Square it, square both sides. So I'm going to square both sides, so x plus 2 equals x squared. How do I solve this? Subtract, let's go the other way. Let's get everything over on this side. So I'm going to subtract minus x and minus 2, minus negative 2, and minus x and minus 2 on this side. So I get x squared minus x minus 2 equals 0. Now I can factor. And my factors have to be 2 and 1, and this has to be negative, and that has to be positive. So this tells me that x equals 2, or x equals negative 1. And we remember that we have to check our solutions. So if I plug in x equals 2, this tells me that the natural log of 4, the natural log of square root of 4 equals a natural log of 2. That makes sense. If I plug in negative 1, I get the natural log of the square root of 1. If I plug in negative 1 here, negative 1 plus 2 is just 1, equals the natural log of negative 1. Can we take the natural log of a negative number? Nope. So this is what we call extraneous. It's not a solution. We checked it in our original equation, and -1 won't work. So our solution is x equals 2. So whenever you get multiple solutions, you have to check your solutions. All right, any questions on that example? Okay, let's look at another one. We're still solving. We have log of x minus log of x minus 3, and that equals 1. Now, if this was 0, if we didn't have anything on this side of the equation, we could just add the log of x minus 3 to both sides and have a log to the same base on both sides. But because of this 1, that kind of messes us up. Anybody see what we might be able to do with this? Think about our rules for logs. What can I do with log x minus log of x minus 3? Right. Subtraction turns into division. So I turn this into log of x over x minus 3 equals 1. So I remember my rules for logarithms here. Turn this subtraction into division. Now I can rewrite in exponential form. So this rewritten in exponential form tells me 10 to the 1 power. We don't have a base here, so we know it's base 10. 10 to the 1 equals x over x minus 3. So that's the same as x over x minus 3 equals 10. 10 to the 1 is just 10. Yeah?
You have found a solution of doing like reverse change of base, add log of x minus 3.
Change of base, and
Do the reverse of that.
so tell me what.
Log x minus 3x equals 1. So x minus 3 is a smaller
Oh,
number.
the x minus 3 isn't our base. Our base here is 10. So when you do the change of base, our smaller number is the base of our logarithm. Here, x minus 3 is just our denominator. Okay? All right, so now we can solve this. I'm going to say that x, I'm going to multiply both sides by x minus 3. X equals 10 times x minus 3. So x equals 10x minus 30. Subtract 10x. And I get minus 9x equals minus 30. And divide both sides by -9. So I get x equals 30 over 9, and I can reduce that into 10 over 3. No. It's nice if you do, though. So this is our solution for this one. We remembered our rules for logarithms, and then solved our equation. Questions on that solution? All right, I just want to do one more example with an application problem that involves investment. And I think there's one of these in your homework. So we talked before about one of the big applications of exponential equations is interest, where we're compounding interest. So we want to figure out how long it would take to double an investment at 8% compounded continuously. So our continuously compounded interest formula is A equals P e to the RT, where the amount is what we get, principal is what we invest, our R is our interest rate as a decimal, and T is our time. So if we want to double our investment, so we start with amount equals P. If we start with P, if we want to double our investment, what do we want to end up with? We end up with 2P. So the amount that we want out at the end is 2P. So 2P is the amount that we want to get, and that equals our original investment times e to the 0.08 times t. So we have an exponential equation here. I have p on both sides. I'm just going to divide both sides by p. These cancel. So I get 2 equals e to the 0.08t. And I want to get t by itself. We want to figure out time. So how do we solve? We have an exponential equation here. How do we solve this exponential equation? What can we do? Take the natural logarithm of both sides. So I say the natural log of 2 equals the natural log of e to the 0.08t. So natural log of 2 equals the natural log and the exponential function are inverses, so they undo each other. So natural log of 2 equals 0.08t. And we divide by 0.08. And t equals the natural log of 2 divided by 0.08. And if we plug that into our calculator, that's approximately 8.66 years. And the thing that's interesting about this, it doesn't matter how much money we start with, because our principal cancels out. So no matter how much money we start with, if we compound continuously at 8%, we'll double our investment in 8.66 years. I think that's kind of interesting. And these are the kinds of applications that we're going to work more with tomorrow and on Friday. Any questions? All right, homework. I was kind of excited. Yesterday, my video views on YouTube went over 1,000.
Video of what, that?
What's that?
Video of that?
Yeah, I post all my lessons for all my classes. It's on 1,000 views.
You're gonna be that next guy.
Right. All right, there you go.